Okay, let's take a look at class example problem unit D3, page 5. This is a very simple example problem application of energy equation. Let's take a look. This is the pumper track. Okay, the purpose of this track is to add energy to the flow so that you're going to deliver the water with 1.5 cubic feet per second flow rate to the maximum elevation of 60 feet above the hydrant. Okay. The pressure right here at the hydrant is 10 psi at the cross section 4-inch diameter. By the way, 10 psi, this is of course gauge pressure. This cannot be absolute pressure, obviously, because if this is a sea level location, pressure atmospheric is typically 14.7 psi. If this is absolute, it's actually vacuum pressure, so it can't. So this is 10 psi G. If you want to add a G here, just go ahead and do it. This is a gauge pressure, 10 psi. Okay? So obviously, this hydrant maintains higher pressure, which is 10 psi higher than the local atmospheric pressure. This is going to be feed the water into this pump. The pump adds more energy, so creating enough pressure here to shoot out the water up about 60 feet. Okay. Now, if head losses are negligibly small, so this problem says, let's just for a moment ignore the head loss. Let's determine the power that this pump must add to the water. Power. Pump power is we want to find out in horsepower. So how much horsepower pump do you need to deliver the water 60 feet above this fire hydrant? Okay? So obviously this is pretty simple example application of energy equation. So let's apply energy equation. P out over gamma plus B out square over 2G plus C out is equal to P in over gamma plus B in square over 2G plus Z in plus HS minus HL. So this is the energy equation in terms of head. Okay? So this is the static pressure head. This is dynamic pressure head. This is just the head. This is the shaft head, head loss. Now, the important thing about this is shaft head. If you have a pump, you need to add HP. This is called pump head. Depending on the device you have, if you have a turbine is the device actually taking energy out, so it's going to be minus HT, if so, it's called turbine head. So this is a pump, so you're actually adding energy. So it's plus. And then I'm going to rewrite HS is equal to plus HP. Okay? So let's just take a look at each term one by one. This is the inflow, this is outflow right here. Pressure, this is, of course, local atmospheric, this is free jet. This is a zero gauge. Velocity outflow right here, velocity here is really high speed, but gradually losing the speed right here. Velocity is approximately zero, reaching the 60 feet, absolute maximum height. So V out is approximately zero. You're losing all the velocity at that height. Z out, let's measure Z from here. Upward positive, this is elevation. If you do that, Z in 0, and Z out is, of course, 60 feet. Right? Okay? P in, it's given, this is a 10 psi gauge. This is a zero gauge. This is a 10 psi gauge. Inlet velocity, can we find that? Oh, of course. Flow rate is given. Divided by cross-section area gets you velocity in. HS is a pump head. This pump head is added head, which is essentially energy added. So how much horsepower do you need is essentially coming from pump head if we determine. For a moment, the program says ignore the head loss, approximately zero. Okay. And also another thing here is B in is of course flow rate divided by cross-section area in. Flow rate is constant. In other words, flow in, Q in, is equal to flow rate out, Q out. Flow rate in is equal to flow rate out. But anyway, Q in is given 1.5 cubic feet per second divided by pi over 4, diameter 4 inch, so 4 over 12 feet square. So flow rate is 17.19 feet per second. Actually, cubic feet per second. No, feet per second, velocity. This is the velocity. Okay? So that's B in. B out is approximately zero. Okay. So this actually makes this equation, the only unknown is HS, which is HP. Therefore, HS in this case plus HP is equal to, this is 0, 0, 60 feet, this is 10 psi, this is known, 0, 0, HS. So HS, which is about HP, is Z out, which is 60 feet, minus P in over gamma, minus B in squared over 2G. Let's just plug in 60 feet minus P in is 10 pounds per inch squared. Let's just convert it to pound per feet squared. 12 inch over 1 feet squared. So this is going to make 1,440 psf. Gamma of water 62.4 pounds per cubic foot. Minus velocity, we found 17.19 feet per second squared. 2 times 32.2 feet per second squared. Okay. So if you punch those numbers into your calculator, this is going to give you 32.33. 32.33. What's the unit? Well, obviously this is a head, so unit is feet. Okay, so this is the answer. Wait a minute, no. The problem is asking you what is the power you need. Okay, so what is the power corresponding to this pump head? This is actually pump head. So you need to convert pump head into the power, horsepower. So this is what we need. W over dot shaft net in. This is essentially W over dot pump. This is gamma times Q flow rate multiplied by HS, in this case HP. Okay, so gamma 62.4 pounds per cubic foot. This is specific weight of water. Q is flow rate given 1.5 cubic meter per second. By the way, this is a CFS, cubic foot per second, CFS. So keep that in mind. Sometimes I specify 1.5 CFS. Please don't ask question, what is CFS in the exam? Because I'm not going to tell you. This is cubic foot per second. Okay. Anyways, 32.33 feet. So this is pump head we found. So this is going to give you foot-pound per second. That's not what we want. We want to convert it to 1 horsepower. It's given by 550 foot-pound per second. Okay? Therefore, this is going to give you, if you punch all of those numbers in, 5.5 horsepower. Okay, so this actually answering the question, what is the power of the pump? Well, my answer is, if you bring like 6 horses with you, it is going to be equivalent to how strong this pump is. 5.5 horsepower. Okay, that's the pump power required to deliver water 60 feet above the hydrant. Okay, this is a very simple application of energy equation. Let's stop here.